Hi, this week I'm going to describe the energy well calculation for a simple one proton and one electron hydrogen atom. So much is said about what are the wells. What do they look like? How are they shaped? What do they do? And I'll try to explain all of that. Now, in this area, we'll talk about just really two of the very top things. What is the atomic model? Okay, it's 3D engineering. And basically, its properties have two forces or accelerations or fields, the electrostatic and the nucleostatic. By nucleostatic, I mean the strong nuclear interaction and the weak nuclear interaction. All right, so the basic hydrogen is the simplest thing there is. It's one proton and one electron. And thereby it gives us the basis of the scale for almost everything else that we do in physics and chemistry. And so you'll see these same ratios used all the time. So basically, you have radial acceleration. So all we're going to talk about is on this axis, we're going to have the distance. And on this axis, we're going to have the strengths. Now understand that in physics, positive is repulsive. It's an acceleration to make the distance bigger, positive. And attraction is negative, and that's to make the distance smaller. It's an acceleration to be smaller. Now, the electrostatic force, which I show here in red, goes negative, and it goes by 1 over distance squared. Okay? So if that was all you have, all those electrons would fall into the nucleus. But that doesn't happen because there's an offsetting force, okay? And it has an extra 1 over r. Now, that was properly described in the math by Bohr, okay? But what he didn't do is he didn't get the correct causation. He said it was a gravitational orbit, which meant the electrons are always going around and around. And that's not true. This is a static force. That is, for every amount that you're pulling it in, you're pushing it out. So that extra 1 over r becomes 1 over distance cubed. Now, at large distances, 1 over distance cubed gets smaller, slower. So this is much bigger than that as we get out here, okay? And so thereby, that's why we call them the nuclear forces, because they are at the nucleus range, and then they become immaterial because 1 over distance cubed attenuates exponentially faster, okay? And the other thing is it's always in the opposite direction. So while this one is an attraction, this one is a repulsion. Things come in these balancing sets in nature, and this is one of them. So attraction at 1 over distance squared and nucleostatic repulsion at 1 over distance cubed. Now the fun math is that when you have the net of these two, when you get less than 1 over distance cubed actually gets bigger than the other one. This is out at 1.5, okay? And that's at that same point only like 1.14, okay? And that's the nature. As 1 over distance cubed goes towards 0, it will become infinity cubed. But as 1 over distance squared goes to infinity, this will become negative infinity squared. And strangely enough, 1 over distance cubed is infinitely bigger than 1 over distance squared, and you get this wall of repulsion. This is the net. The black line here is the net of the electrostatic red force and the nucleostatic green force. And that becomes a wall of repulsion inside 1. And 1 is the balancing point where both of those are equal. And that is known as the Bohr hydrogen radius. It's also used as the symbol A0, sub-0. And you'll see that A sub-0 throughout our paper. So this basic balancing is critical to understanding how the electron wells look. If you get too close, you hit this wall of repulsion, you're pushed back. Now, the funny thing is that if you're pushed too far, the net is bigger, but guess what? Because this gets far faster as you go out distance, after you get past 4 or 5, the net attraction is exactly equal to the electrostatic. And of course, that's why no one figured it out, because every piece of equipment that we measure only gets the electrostatic, and it eventually they get the correct answer. So nobody bothered to think about this until Bohr did the correct math with the wrong physical model. So how deep is that energy well? So first, let's do the perfect calculation here, okay? So the radioelectrostatic is 1 proton, positive, and 1 electron, which is negative. So it's a negative attractive force. Now the constant, and I'm using here the shortcut of the Coulomb constant, but done in per particle. Understand that I eliminate mass in my other paper and get to only particles and no mass, but that's for a more advanced class, okay? This is the Bohr distance, e to the minus 11. That's very tiny. That's 10 zeros and then 5.29 after 0 meters. Now the thing is, you actually square that and then multiply by this. And so you get that scaling factor. And from there, you get the repulsive force. And this is in kilogram, because we're still using mass here, meters per second, okay, squared. And that's an acceleration. Now, for the radial nucleostatic, that's the strong nuclear force in your old textbooks, but I teach it as radial, and this opposite extra 1 over r, those are 1 particle times 1 particle. Remember, there's only 1 nucleon and a hydrogen. That's why we're using this. It's a very, very simple model. And the constant is here. That comes from my other paper. The distance is the same, but this is cubed instead of squared. So thereby, you end up with exactly the same, and the electron doesn't move. Well, that's exactly what happens here. Okay? Now, so this is the bottom of the well. The electron at this point would be perfect. Now, the world is not perfect. There would have to be no other particles in the entire universe if you wanted to get this situation, because gravity or something from something else will knock it out of this position. So let's see what happens to this energy well. And for that, I'm going to take that distance and I'm going to change it by 1 particle. 5.29 times 10 to the e, 5.29, but 1, 2. So I'm going up by the 2 point something in this 5th digit, which is the size of a radius. So I'm only moving that a little electron, 1 electron over, okay? And let's see what happens to the force, okay? So again, -1, same factor, new distance, so the square is a little difference, and that comes to this number, okay? Now, this is slightly different, and that comes to that, but now I have a net, okay? Remember, I moved this away. It's slightly larger than this. But now the acceleration is inward. Of course, that makes sense based upon this graph, because I moved here. Since I made the distance more, it becomes slightly negative, which then loops it back. And if I get too far in, it pushes it repulsive. It's a positive, pushing that distance back in. That's why this is a self-sustaining model. The static, electrostatic, nucleostatic, 2 radial force model is a self-sustaining model for nature of the universe at the proton and electron level. But now there's this extra tiny force. Now it's only about 1 to the 4th, smaller than that, but it is negative. So I increase the space, but the force is negative. Okay, how bad is that force? Okay, I've gone out here, I'm looping back down. I moved one particle, and that will move that back. This is in kilogram meters per second squared. So how many particle radiuses will that move me? Well, in 1 second, that will move me back 1,500 particles. So it's like a big spring. If I push it like this, it's going to go out 1,500 the other direction. Okay, that's a huge force. This is not a little well, a nice big slooping, pendulum moving, which is what we're taught. Force. This is bang. Of course, is on the other side. Okay, and it will push right back to the middle. And eventually this attenuates back to hopefully as close to this as you can. Okay, this is huge. Now that is not a big movement. Okay, this is a tiny movement. So let's see what that looks like. 1557 particles. Okay, let's see that. So now if I had a well and it have 1,500 radiuses of the electron, down here would be 1, and the wall would be 1,500. Now, the slope of the wall on the left is 1 over distance cubed. That's a little steeper than the 1 over distance squared wall on the other side. But this tiny space of, say, 1 or 2 electrons at 1.2 radiuses is in a well 1,500 times bigger. Now, I like to do this as 18,778 because that number is actually important lots of other places. In which case, the basis would be 0.12 meters. So you would be standing in a well and able to move 3 or 4 inches in this side or that side, and you'd have to climb up 1,000 meters to get out of that well. Okay? Electrons, now, these can move, but let's see. So that particle can move down there. I can move side to side. I can rotate around, okay? But not really a whole lot. For all practical purposes, electrons have stable positions in relation to the proton and the nucleus at the center. It's a little more complicated when we add neutrons in there, but the nucleus is the core. And the bouncing around is not a big space, okay? That bouncing around has lots of things. And if you can read the Zitterbewegung by Schrödinger or monopole work by Dirac, and maybe my work converting monopoles into duopoles, you can find calculations of this little tiny thing. But for all intensive purposes, electrons are locked in a 1,500-foot well with about 2 or 3 inches of movement available and turning. And yes, they're not exactly in that one place, but they aren't moving very much. So why is this important? Well, if you go look in your textbooks right now, they'll talk about the fuzzy balls and the electron distributions, okay? And I show these electron distributions as 2 rings of electrons at longitudinals, so basically at the end caps of a cylinder, 2 cylinders on each side of the nucleus. And that distance is this 18,778 divided by 12, okay? And that's the size of that green ring. And so I actually disagree with your textbook that it's this big fuzzy ball. I think these are pretty tiny little rings. Now, I don't know whether the electron's moving this way or that way. Okay, so this is what I believe those fuzzy balls are actual distributions. Unless they get bounced out of that well, they're pretty much in a very tiny range. Okay, now the electrons can be here or they can rotate around because what I did was I did radial energy. So this is the amount that is out. If I go in any direction, those equations didn't change. So I can be in these 2 end cap. Now I can be anywhere in this longitudinal ring, and the math that I just did is very stable. Though they're going to say at the same angle and the same distance, within that 18,778 ratio with the appropriate parts. Okay? So now, if you want to go into the advanced courses, you'll understand that fuzzy is being calculated because they're using the density as the 1 over minus g. And that goes into very complicated stuff like Einstein's general relativity, okay, where they're not under, they're using the electron versus length, but here you're at the electron, so that calculation changes, making them calculate this as too fuzzy. So what is that ratio? Why did I use and like that 18,778? Well, that's the ratio of the edge of the particle versus A sub O, the Bohr radius. So this is the equilibrium versus edge scaling factor. Now, in the old textbooks, you'll see this wrongly called the fine structure constant. It's not a constant, it's a ratio. It's a ratio of two distances. And one of those distances is the equilibrium, and the other one is the edge, because that's the point of the maximum strength of those. But we're not taught the maximum strength. We're only taught the strength at A sub O. You see, Planck is the strength for both electrostatic and nucleostatic at the Bohr radius. Here's the calculation. They both come to the same magnitude, but opposite signs. And at A sub O, which is this distance here, they are equal. And so for so many calculations, you can use that wonderful calculation of this ratio. And that ratio is 18,778. And of course, the square root of it, because I'm doing that, is alpha, or alpha sub E, which is called the fine structure constant. Notice I cross it out because it's not a constant, it's a scaling factor. Now, most of the time in my schedules, I'll actually replace one or other of these because the formula that I'm doing has an actual distance. And because I know this ratio and I use alpha, I know which one to scale and which direction it goes. Okay? So this is all part of knowing the different fields in there. There are potentials, accelerations, or forces, and fields. They're 1 over r squared and 1 over r3. As fields, they're 1 over r cubed and 1 over r4. And the ones that we're concentrating on is the balancing of the forces at 1 over r squared and the extra 1 over r at r cubed. So these wells are very, very deep. And in 1,500 seconds, you would be so far on the other side that it's just not even worth thinking about. These things attenuate, and the time is a nanosecond of a nanosecond for it to go to the other side and then push all the way back, okay? But you will see this 18,778, or the square root of it, the 137, all the time. But you understand it's the ratio of two distances. Finally, you also have to understand that these are not perfect pendulums. You'll find many of the old textbook things that have these as a nice calculation as if a pendulum. But one side is bigger than the other, so it's okay? That's not the same, okay? So don't expect perfection in subatomic models. You can't know what's going on in that tiny space at the bottom of the well. And those differences, like how it rotates, of where the angle is of that duopole or monopole, is important to other calculations because rotations cause wave functions. So these particles have both linear and rotational errors that make us that the things are not continuously in exact position. But for anything that you're trying to calculate in chemistry, if you could get precision down to 1 over 18,778, you'd be crazy. No, most of your chemical reactions, if you know within 40% if it's going to bond or not, it's usually huge changes, okay? Not these tiny changes, because that it'll probably seem like it's never reacting. You want reactions that are 50%, 80%, coming out of those bonds to create a chemical reaction. To get out of that well is the only way that you're going to have a chemical reactions. So, and then remember that your textbook, massive electron distributions, these fuzzy balls are an exaggeration and they're a misinterpretation, but they're generally correct. Don't believe that they don't have years of experience and that you can't get value by leading them, okay? You're just never going to get an exact value, but it's not also going to be that electrons can jump to Jupiter, okay? On this size well, that electron, not possible. It's not possible by this math, and it's not possible by the speed of light, okay? Things do not go more than the speed of light, as much as science fiction and other things will tell you. So I hope that this gives you an idea of how I believe that an atom or a molecule is really a locked-in set, that it's not jump to Jupiter. It is a locked-in set. Now, that whole set may be rotating very fast, say in a gas state, that it looks just like a big sphere. But for what we're doing, consider electrons have specific angles, like, crystals. And remember that those positions are within the 1, 2, 3, 4, 4 decimal points. They're pretty much in the same position unless you really throw a lot of energy, like a photon hits it directly. That unless you do that, those are going to stay in these deep, deep wells. Thank you.